All right, this is Exus the Podquest, and this is a special introduction to an interview that you're about to see with astrophysicist Ethan Siegel about the James Webb Telescope and his book about it named Infinite Cosmos. And Ethan is returning to our show specifically to talk about the telescope, but the telescope itself and the project surrounding it touches on a theme that I want to develop much further as we go ever forward on this show. And that theme is how far we've come. If you think about it, human beings started as rudimentary life forms on the planet, basically unicellular entities that grew and developed and evolved over extraordinary periods of time. But now here we are. And here we are today being able to do something as extraordinary as putting a massive telescope together and sending it out to an ungodly distance to orbit the sun along with everything else that's orbiting the sun and not interfering with everything else, and to manage all of that and to start out by taking material from the actual Earth and forming it into glass and metal and whatever else that the gold and beryllium, all the stuff that goes into the actual building of the telescope. We're able to do that. We're able to put all those things together and to have all the engineering and to develop the rocket that sends it out into space. It's just so astounding and so mind-bogglingly complex that it boggles the mind, and it's just something that I really, really find extraordinary, and I want to develop that as a theme throughout his time. And if you didn't see the episode previously about cosmic evolution, go back and take a look at that. But in the meantime, enjoy the show. You're going to love this interview with Ethan Siegel as we go ever forward. All right, welcome to Exus the Podquest. We are thrilled to have back a guest back on the show. It is Dr. Ethan Siegel, theoretical astrophysicist, Dr. Ethan Siegel. He's going to be talking about his new book, which is Infinite Cosmos, Visions from the James Webb Telescope. How exciting. It's got a foreword by Brian Greene. It's got all the trimmings. Just can't wait to talk about this, but we're just going to wait for a second while I do the quote of the day. All right, here we go. Like buried treasures, the outposts of the universe have beckoned to the adventurous from immemorial times. Princes and potentates, political or industrial, equally with men of science, have felt the lure of uncharted seas of space. And through their provision of instrumental means, the sphere of exploration has made new discoveries and brought back permanent additions to our knowledge of the heavens. That's by George Ellery Hale. He's an astrophysicist of his own, in his own right, and he contributed significantly to the advancement and development of a number of significant telescopes. Our guest today, as I mentioned, is Dr. Ethan Siegel. He is I'm going to repeat his resume because it's so incredibly impressive. He's a theoretical physicist, astrophysicist, a science writer, and science communicator. He has a PhD in astrophysics. Keep saying it. Astrophysics from the University of Florida. He's taught many university-level courses, among others at Lewis and Clark College in Portland, Oregon, and the author of 2 books, now 3 books. The 2 first ones, Beyond the Galaxy, second one, Treknology, and now he's adding on this new one, which we're just really excited about talking to him about. He's the creator of a very popular science blog named Starts with a Bang, and he's written tons of articles in places like Physics Today and Scientific America, Astronomy Magazine. He has this ongoing articles series that I mentioned last time that I just really love. It's called Ask Ethan. That's how I was introduced to him, where I first learned about him. People will ask him questions about incredibly technical things, and he then provides extraordinary answers in not so technical terms, but sometimes gets into that too. Anyway, that's Ask Ethan. And as I said before, I have the privilege of asking Ethan lots of questions about the James Webb Telescope and his exciting new book. Welcome to the show, Ethan. Love having you back.
Thank you so much. It's my pleasure to be back here on the Nexus podcast. And the James Webb Space Telescope for me is something that has captivated my imagination for many years, since way, way back before it was launched. In fact, it was my Halloween costume about 4 or 5 years ago. I dressed up as the James Webb Space Telescope. And I remember when it launched back on Christmas Day of 2021. It was one of those events that I myself woke up at about 4 in the morning so that I could watch the live stream of it happen. And, it's hard to believe that it's barely been 2 years since JWST started its science operations, because here we are in 2024 and it has already revolutionized how we think about the universe. And I'm really excited to share that today with you and your listeners.
I understand that the book it was something that the National Geographic asked you to write. Is that something that I've got correct?
That is actually true. This is a National Geographic book. It is my first National Geographic book, and I was so excited when they asked me to partner with them to put this together, because it meant that not only was I going to be able to reach a new and larger audience than I generally do with my books and blog and the other endeavors I do, but it also meant that we were going to be able to be partners in figuring out how we told this story, what images we used, what types of design and layout the book would be able to have, because National Geographic has such a great stable of behind the scenes people who work to make these books as high quality and beautiful as as they're known for being. And so when this opportunity came along, it was an intersection of many things I was excited about, and it was a labor of love to be able to put it together. And I'm so excited to tell everyone out there that this book comes out on October 8th, which is not very far away. And you can already pre-order it on places like Amazon and Barnes and Noble, and I promise you won't be disappointed.
Oh, that sounds fantastic. Is it also available on your website? I would imagine you might want to throw that out there if it is.
I wish it were. I don't
Oh,
have the ability to sell directly through my website,
oh,
so
gotcha.
you'll have to go to the official outlets or wait for the book to be released. That's part of my contract with National Geographic, is no direct sales from the author.
Oh, gotcha. Okay. Yep. Well, Amazon, Barnes and Noble, everyone go out and get that book. Again, it's the name of it is Infinite Cosmos, and it's talking about the James Webb Telescope. Now, Brian Greene, I understand, wrote the introduction to the book. How did that come about?
Yeah, so National Geographic said, we have you to write this book, Ethan, but this is who we want to do the introduction. And I've given talks at Columbia. I know who Brian is. Many of your listeners will probably be familiar with the Elegant Universe. And even though Brian is a string theorist, he's extremely well versed in a large number of areas of physics. And I've had a chance to read his introduction. And you have to remember that the whole point of building the James Webb Space Telescope is not like, oh my goodness, we have no idea what's out there in the universe. No, it's that we've looked at the universe in glorious detail for decades now, with 19th, 20th, and 21st century astronomy tools, ground based telescopes, space telescopes, telescopes that span the full gamut of wavelengths from high energy gamma rays down through visible light into the infrared and all the way into long range radio waves. So when we were talking about what will the James Webb Space Telescope bring to us, it's not like, oh my goodness, we'll see the universe for the very first time. It was, we will see the universe in this specific set of wavelengths of light, with higher resolution, sharper imaging, more light gathering power, the ability to see fainter objects and more details in those objects than ever before. So some of the cosmic records we were expecting are: will we find the most distant galaxy we've ever seen? Will we find the most distant galaxy cluster ever seen? Will we be able to see features in planet forming disks, star systems, galaxies, and in the large structure of the universe than we've ever seen before? And the answer to all of those is absolutely yes. Those are some of the rewards we've reaped so far. But as always, when you build something new with better precision, higher accuracy, more light gathering power, superior resolution, when you see the universe in wavelengths of light in particular ways that you've never seen it before, the thing you get most excited about is what we call discovery potential. It's I'm going to look at these things that in ways I've never looked at them before. I'm going to look at these regions of sky, at these objects, etc. And who knows what I'm going to find? I have a set of expectations, but sometimes the universe surprises us. And we've already gotten a whole bunch of those surprises when it comes to the James Webb Space Telescope. And those were some of my biggest goals with this book is let's tell you how the James Webb Space Telescope was designed and built and why it was designed the way it was, why it has these capabilities that no observatory before it ever had. Then I want to take you on the journey of it was launched and it deployed and it was calibrated. How did we do that? How did we hit those milestones? How did we get this observatory from being a folded up payload in a rocket to being fully deployed 1.5 million kilometers away from Earth? And finally, what did we see? When it opened its eyes on the universe and it started looking at these objects and taking data and collecting information about what's out there, what did we discover? And it was my goal with this book to take you, the reader, through all of it and bring you right up to the frontiers of what we know today.
Very cool. We're gonna definitely dive, of course, right into the book. But before we do it, just a couple of curiosity points. One is you mentioned the wavelengths, and I understand that what the James Webb Telescope is doing is using infrared wavelengths. Is that right? And if so, um, pardon me, but if you could let us know what does that mean? What is infrared wavelengths versus any other kind of kind of ground up
So
pulse?
if you stand in front of another person and you look at them, you can see what they look like. Um, and if you close your eyes, you can no longer see them. But if you were to put your hands near another person, not touch them, but just put them near another person, you'd actually be able to feel their presence because even if you closed your eyes and you blinded yourself to looking at them, the human body is a warm blooded body. We don't emit visible light of our own. If you turn off all the lights in the room, you won't be able to see me or yourself or each other or anything. But even in the absence of light, you are still emitting heat. We are warm blooded creatures. We exist at about 98.6 degrees Fahrenheit, and we radiate in the infrared. All right. So infrared is just a form of light. But whereas visible light comes in this very narrow range of wavelengths from about 400 nanometers to about 700 nanometers, that's the light we can see. But at longer wavelengths than 700 nanometers, that's where the infrared comes in. And the problem with trying to see infrared with something like a ground-based telescope or with something like the Hubble Space Telescope, which was, our most powerful tool to view the universe before the James Webb Space Telescope came along, those are predominantly best done with visible light. Why? Because you have atoms and molecules making up everything, including your telescope itself. And here on Earth, we have a relatively warm environment, right? It doesn't drop down to absolute zero at night. It doesn't drop down to hundreds of degrees below freezing. It stays in a modest temperate range where we're very comfortable. That's good for life, right? That's good for conditions for creatures like us to survive and thrive. But it's not great for viewing these longer wavelengths of light because when you heat up anything, atoms, molecules, including your telescope and its instruments, you get what's called thermal noise. These moving atoms and molecules, even on a microscopic scale, they still have energy to them. So if you were to look at the world in infrared light, you would see, oh, these are all emitting infrared light. Anything that gets heated up is going to emit infrared light. So we want to see things in the universe that we've never seen before. That means, well, yeah, we can always build a bigger optical telescope or a higher resolution optical telescope, and that's one way to do it. But we can also look with observatories that are optimized for all the different wavelengths of light. This is really important if you want to see far away, because
Mhm.
one of the things that happens in the universe is the space between distant galaxies and groups of galaxies and clusters of galaxies. The whole fabric of the universe is expanding. And when light travels through the expanding universe, the wavelength of that light gets stretched to
Mhm.
longer wavelengths. So if we want to see the most distant things of all, we have to account for the expansion of the universe. And that means it's not enough to look invisible light, because even ultraviolet light, right, that light that damages us from the sun, the most energetic, shortest wavelength light from the sun, if you emit something that's ultraviolet, but it travels through the expanding universe, its light's going to stretch and become visible, and it's going to stretch more and more out of the visible part into the infrared. Hubble, in orbit around Earth, can only see a little bit into the infrared. So part of the goal for the James Webb Space Telescope was to, number one, put it farther away from the Earth, way farther away than the Hubble Space Telescope, so that you don't have the heat from the Earth contaminating it. A second thing is we had to build a giant sunshade so that the optics part of the telescope, the mirror and the instruments, always were shielded from the sun. So you had to build a novel 5-layer sun shield to cool the observatory. In fact, one of the instruments aboard the James Webb Space Telescope is looking at such long wavelengths of light that it needs its own active cooler on board that uses liquid helium to keep it cold. So we do all of this so that the James Webb Space Telescope will be optimized for viewing the universe in these long wavelength infrared sets of, to view this type of light. And once we start seeing that, we want to make sure that we're not contaminating it with this thermal noise, that we're not contaminating it with this heat energy. So this is why it was such a challenge to design the James Webb Space Telescope uniquely to have the properties it has so that we could see the universe as we've never seen it before.
Wow, that's absolutely fascinating. You talk about design and kind of constructing the telescope. Who was responsible primarily for designing the project?
It's a huge collaboration of a lot of different people, a lot of different teams, and a lot of different organizations. NASA was involved, the European Space Agency was involved, the Canadian space industry was involved. Or sorry, the Canadian Space Association was involved. Um, we had 4 main instruments, all built by different teams and different groups, some government, some scientific. The launch vehicle was procured by the European Space Agency and was manufactured by Arianespace. The various components were built by corporations. Ball Aerospace helped build the blanks for the mirror. We had Northrop Grumman was the project manager. Northrop Grumman was responsible in the end for the complete design, assembly, and marriage of the different telescope elements together. And there were literally thousands of scientists, technicians, and engineers who worked on this, including people at various clean rooms at various space centers across the country that made sure that this telescope was kept clean, was kept pristine, was tested over and over again for will its components correctly deploy? Will it survive the rattling and vibration and the temperature changes experienced during launch? Will it be capable of surviving the deep, conditions of space far away from Earth? Will it be resilient against all of these different stresses it's going to experience? Will it be resilient against micrometeoroid strikes and the tiny little, pieces of space dust that will run into the telescope? We had to test and prepare for all of these things because with something as intricate as the James Webb Space Telescope, we had to make sure we get one shot at this. We have one JWST, one chance to launch it, one chance to deploy it, one chance to calibrate it, and one chance to get it taking science information. And if we had any point of failure, and there were hundreds of potential points of failure that were identified. Sorry for just a moment.
That's your dog, James Webb, right?
Yes, he sure is something. So we had hundreds of points of possible failure that were identified. And all of this continued testing and all of this continued inspection and the various ways we had of like, oh, we saw something that's potentially hazardous. We're going to come back and make sure that all screw fasteners are replaced and that the vibration testing can be done successfully and that we don't have any cryogenic problems. They even developed a new type of carbon dioxide snow to remove dust and dirt from any of the mirrored surfaces just in case it was needed. We took all of these precautions so that when the critical time came and the James Webb Space Telescope was loaded into its rocket, was launched into space, and was deployed, we wanted to make absolute sure that our chances of a successful mission were maximized.
Wow, I mean, it's absolutely amazing. It sounds like the project was like extraordinarily daunting, and putting together the team and all of the various parts of it. I mean, I mean, obviously have the top people working on something like this. I mean, if I get a box of delivered to my house and it's got furniture in it that I have to assemble, it's going to take me forever, and I'm going to screw it up. So obviously, you need the best people on something like this. Is it a I mean, obviously, a project that's taking years to do. How long did it take to put this thing together?
Arguably, I would say the James Webb Space Telescope was conceived way back in the 2000s, like in the aughts. And its design changed and evolved over time. They realized, well, one of the things we're limited by is how big is the rocket that's going to launch it. Originally, they said, let's just build one big mirror. And then they said, no, you know what? If we can build segmented mirrors, then we could fold the telescope up and fit a larger, higher resolution telescope inside a rocket than if it just had a single, what we call a monolithic mirror. And they said, let's do it. Let's be ambitious and let's build this segmented type of telescope, which we've only ever built on the ground before. Let's build one and send it to space. They said, hey, we want to have this big thing and we want it to be cold enough to view the universe in these long infrared wavelengths of light. What do? They said, we need to build a sun shield, a novel 5-layer, like tennis court sized structure where between each of the layers, it shunts heat out and makes the next layer colder and colder and colder. It's amazing that even though the hot side of James Webb Space Telescope is in direct sunlight, the cold side is only at about 40 Kelvin. It's cold enough to freeze liquid nitrogen over on the cold side, and that's
Wow.
just from passive cooling alone. So the idea of a folding telescope, the idea of a giant sun shield, the like all of these ideas, this was NASA and a lot of other people who were involved with planning it being ambitious. They said, we have this way we want to view the universe. We want to see this high resolution. We want to have this big light gathering power. We want to have unprecedented precision. And so they said, let's be ambitious. James Webb Space Telescope actually turned out to be, because they made improvements across the board in how they handle space telescopes, it turned out to be the cleanest space telescope ever launched. No space telescope has ever been launched with smaller amounts of dust, dirt, and debris on their mirrors and inside the telescope than JWST. And that was because in all of this, they also improved clean room technology for building the James Webb Space Telescope. This was, I would say, a Herculean effort across the board to get something as good as this. So it wasn't just, oh, like time improved, technology improved. People had the vision to say, let's try and do something remarkable that's never been done before. And at every step of the way, if something was wrong, they caught it. They tested it and they caught it. You might remember the famous Gene Kranz from the Apollo era, failure is not an option.
Oh, yeah.
That's ex- that's exactly how NASA treated this.
Wow, that's really extraordinary. We are coming again up against our halfway clock, but I wanted just for a couple seconds, if you can give us a quick shot about the difference between this telescope and the one that everyone has heard of as well, which is the Hubble telescope. You mentioned it a little bit, but a little bit more on that.
Sure, let's do side by side. Hubble's mostly visible light. It can see a little bit into the infrared. If you want to know what that means in terms of wavelengths, we were talking about nanometers before. Well, 1,000 nanometers is 1 micron, and Hubble can see out to about 2 microns. Hubble's about 2.5, maybe 2.4 meters in diameter, and it's one single mirror. It's basically a tin can in low Earth orbit. It completes a revolution around Earth in every 90 minutes or so. The James Webb Space Telescope can see much farther into the infrared. Instead of up to 2 microns, it can see out to about 30 microns in wavelength. It can see about 15 times longer wavelength light than Hubble can. Instead of being a 2.4-meter diameter mirror, it's a 6.5-meter diameter mirror. It has almost 3 times better resolution and about 7 times as much light gathering power, which means if you want to see a faint object with Hubble and you look at the universe for a week, you can see that same faint object with the James Webb Space Telescope in a day rather than an hour, and you'll see it about 3 times sharper than you could with Hubble. Instead of being in low Earth orbit and just covered in basically tinfoil to reflect sunlight away, it's located 1.5 million kilometers
Wow.
away from Earth, orbiting a special gravitational point known as the L2 Lagrange point, so that as the Earth orbits around the sun, that L2 Lagrange point stays at the same distance away. So the telescope follows us in space as we orbit around the sun. So,
Wow.
and James Webb Space Telescope had this giant sun shield. Hubble doesn't have it. James Webb Space Telescope, for Hubble, it has gyroscopes, and James Webb Space Telescope also has gyroscopes. The biggest difference is James Webb Space Telescope cannot be refueled.
You were saying that Ethan, that the Hubble is located close to Earth, and that the James Webb Telescope is located about 1.5 million kilometers away from Earth. That's a long distance. What is that in miles? Is it about 900 or 1 million miles away?
It's close to 1 million miles. It's about 930,000 miles. So we're talking about a really long distance. It's about 4 times as far away as the moon is from Earth. So we're talking about something that's significantly farther away from us than even our moon is from us.
Wow. Okay. And how far? I mean, we were talking also about the mirrors that the telescope has, and then does it use those mirrors? How does it use the mirrors to look into space? And then how far can it see? How far out?
So that's a really good question when you ask like how far can it see? Because how far it sees is dependent on two things. Number one is that wavelength of light we were talking about. So as the universe expands, which it's been doing since the Big Bang, um, the earlier an object emits light, the earlier in cosmic history an object emits light, the more the expansion of the universe is going to stretch that wavelength of light. So this is part of the reason we use James Webb Space Telescope where it is so far away rather than being in low Earth orbit. In low Earth orbit, your telescope, yeah, sometimes it's in direct sunlight, sometimes it's in the shadow of the Earth, but it always has the heat radiated from the Earth to contend with. Being almost a million miles away from the Earth means that that heat from the Earth will have dissipated, will have spread out so much that the Earth isn't going to appreciably heat your telescope anymore. That's part of the reason that we would put James Webb Space Telescope so far away.
Wow. Okay. So yeah, and that makes obviously great sense. But from a kind of a layman's perspective, when you're sending a rocket with a telescope on it out into a million miles away, how was it calibrated? I mean, even calibrated. How was it determined or predicted that that object, once it was released, it was going to stay in orbit or whatever it is, alignment, so that you can actually make it work and communicate with it?
So this is part of the we do ambitious things aspect of the
Hmm.
story. If you want to have your telescope be at this L2 Lagrange point, right? You have to recognize that we have the sun and we have the earth and we have gravity at play. The earth is going to orbit the sun once a year, pretty standard stuff. But the reason we talk about the L2 Lagrange point, and there are a total of five Lagrange points, but the L2 one is the one that is on the opposite side of the Earth from the sun. It's the only one like that. What happens is as the Earth orbits the sun, the L2 Lagrange point stays in that same relative position. So if you're on Earth, putting something in orbit around the L2 Lagrange points ensure that when it's night on the Earth, you can see something that's at the L2 Lagrange point and you can talk to it. And that's one of the things we do constantly. The huge advantage of being out here is okay, first off, unlike in low Earth orbit, you're not behind Earth half the time. Second, out here, as we talked about, you get less of the Earth's heat, so you don't have that interference problem. But the third thing that's really great about being out at the L2 Lagrange point and why you want to be there is once you get there, it's a gravitationally stable point. So you can spend all your fuel once you're there pointing your telescope and conducting science operations. Getting there was the hard part. So, how do you get there, right? That's what you asked. How do you get there? Well,
Hmm.
you have your rocket put you on a trajectory that once you get into space, it has you mostly on your way towards L2, but you need thrusters on board. And this was one of the big things people were worried about at the moment of launch. Any imperfection in your rocket's initial trajectory is something that you're going to have to make up for by burning spacecraft fuel. The rocket that launched the James Webb Space Telescope was an Ariane 5 rocket, and they had over 80 successful launches in a row. And then shortly before they were going to launch the James Webb Space Telescope, one of the rockets had a problem and it actually launched in the wrong trajectory just by a small amount, a few degrees. That was enough that if that happened to the James Webb Space Telescope, it couldn't have reached the L2 Lagrange point. There wasn't enough fuel on board it. So we realized when we launched this thing, wow, the better a launch we have, the longer of a mission because the more fuel we'll have when it gets to L2, when it gets to that Lagrange point. So a better launch means a longer lifetime, and a worse launch means a shorter lifetime. In a worst case scenario, no lifetime at all. So that moment of launch was going to determine how long of a science mission we're going to get out of it. And what people were hoping for is that we would get at least 5.5 years. You want that extra half because that's how long it takes to calibrate and commission your observatory. And we were hoping to get at least 5 years of science operations. And most people were hoping that we'd get more like 10. Do you
Wow.
want to know what happened when we actually launched it?
What happened?
The launch was so precise. It was so on track that the first thing we were expecting to happen after the spacecraft separated from the launch vehicle was we were expecting to wait about 5 minutes and they would deploy the solar panels and then they would make their first course correction burn to get them towards L2. What wound up happening is just seconds after the spacecraft separated from the telescope itself, the solar panels automatically came out because the sensors on board the telescope said, "You gave me a perfect launch. I'm already on track to go right to L2. I don't even need to make a spacecraft burn. I don't need to use any fuel." The solar panels came out, and people who were in the know who saw that knew exactly what it meant. Since JWST arrived at that L2 Lagrange point, the perfect launch saved it so much fuel that we are expecting more than a 20-year science lifetime from it, somewhere between 22 and 23 years. So this is truly going to be the space telescope of this current generation, just like the Hubble Space Telescope was humanity's flagship observatory for the 90s, the aughts, and the 2010s.
Wow. I mean, it's just absolutely astounding to me. These gigantic minds are just all working together. I can't even imagine the amount of intellect and technical skill that had to go into this. And then, to get it out there, like you were saying, 930,000 miles away. And then it's communicating. I mean, is it communicating with people like here on Earth on a regular basis? Does someone like got a controller and is moving it about to tell it what to what to look at, or is it doing it on its own?
There is a command center. So over in Greenbelt, Maryland, at the Space Telescope Science Institute, they have headquarters for the James Webb Space Telescope. This is where deployment was conducted. This is where the instruments were calibrated. This is still where they send commands to the spacecraft and say, hey, point in this direction and set these filters and set these parameters, do this calibration, and now go observe this target in the sky. And then switch your filters to this other set, do this calibration, and observe this target in the sky. And all of this is conducted here on Earth. It's kind of fun when you think about it. That spacecraft isn't going to respond instantly because by time you decide what you're going to do and you send your command there, it takes about 4 seconds for that signal, even at the speed of light, to arrive at the telescope. So you actually have to think here on Earth when you are programming what is that telescope going to do, you're giving it commands for its future. And when that telescope is telling you what it's doing right now, you have to realize by the time you get that information, that telescope is telling you what it did in the past about 4 seconds ago.
Wow.
So, in order to keep everything working the way it should, we need to have James Webb Space Telescope do some automated things that it keeps track of for itself in real time. And then we give it the commands to say, and on a slight delay, do this.
Wow.
So we control it here on Earth, but it has some autonomous abilities on its own to say, when these conditions arrive or when my conditions fall out of these range, here are the things I'm going to do on my own without waiting for commands back from home.
Wow. Just awesome. Now, you would the one of the sections of your book, probably the one that's most entertaining to people, and that we really want to read, is what has it seen so far? What have we gotten in the last 2 years from the JWST? What do you have?
I mean, if you have not been paying attention to the pictures coming out from the James Webb Space Telescope, I encourage you to not wait for the book and go on the internet and go look at some of the JWST images that it's shown us, because these are spectacular. Not only are they just visually stunning, but they are showing us details about a whole variety of objects in the universe, from planets in our solar system to newborn stars and stellar systems elsewhere in the galaxy, to entire galaxies of their own, to even giant collections of galaxies from the distant universe. It's showing us things we never even knew to look for out there. For example, we have already discovered new storms on planets like Uranus and Neptune, right? The most distant giant planets in our solar system. We've imaged them with JWST, and the only time we ever got better images of Uranus and Neptune was when Voyager 2 flew past them in the 1980s. So we've already discovered new features on these planets here in our solar system. We've already said, hey, I want to try and see what's the farthest galaxy I can see with the James Webb Space Telescope. And not only has it already broken the old record from the Hubble Space Telescope, but today, if you would say, what are the farthest galaxies? What are the most distant galaxies that we know of? That old record holder from Hubble isn't even in the top 10 anymore. All 10 of the top 10 most distant galaxies we know of came from the James Webb Space Telescope. My favorite surprise discovery, something we weren't expecting, is we said, hey, I want to take the James Webb Space Telescope and I want to look at a young planetary system. This is a star that's maybe only a few 100 million years old that has young planets orbiting it. It still has a bunch of dusty debris in it. If we were to look at our solar system back when it was that young, we would have discovered, like, oh my goodness, there's like asteroids and all of this planetary debris everywhere, and it's still colliding with Earth and all of the planets. This is a period known as the early bombardment of Earth. That's what it corresponds to. We looked at this other system and we said, well, it's probably going to look like ours, right? It's going to have some inner planets. It's going to have the equivalent of an asteroid belt. It's going to have some outer planets. Then it's going to have the equivalent of a Kuiper belt. That's what we expected to find. Guess what? We looked at it, and what JWST saw were three belts, not two. There was an asteroid like belt and a Kuiper like belt. And then somehow there's what we now call an intermediate belt. And because this is the first system we've ever looked at like this with the James Webb Space Telescope, we don't even know what's typical. Do solar systems, stellar systems form with multiple belts? Do most of them have two? Do most of them have three? Is there a different number that most of them have? We didn't even know to ask this question. We thought we have two. The physics we understand said, oh, yeah, I understand why I'd expect there to be two. Then we go look at our first system and we find it has three. So there are a lot of things on small scales as well as on large cosmic scales that the James Webb Space Telescope has really surprised us with. We've also found the most distant cluster of galaxies, where we see more than a handful of galaxies all bound together. The James Webb Space Telescope broke that record. We also found the most distant, what we call a gravitational lens, where we look out at the universe and there's a bright, massive object here. And then behind that massive object is more objects. And when the light from that object passes near, the object that's intervening, that foreground object, it actually bends the light from it, sometimes into multiple paths. So you can see the same object with different images, or you can see the same object stretched out into an arc or even a ring. The James Webb Space Telescope has shown us the most distant gravitational lens we've ever seen. Um, and as time goes on, it's just discovering more and more and more details about the universe, more objects that we didn't know would exist or have the properties that they do. And even though the book is in its final form right now, we're continuing to discover new things, and we fully expect to, just like we did with Hubble, for years and decades to come.
Wow, how exciting is that? And doing the research for this interview, I came across a reference to the James Webb having really come across newly discovered exoplanets, which are kind of exciting to people who are into the potential for life on other worlds. Tell us a little bit about that, if my research was accurate on it.
Your research is accurate. It has discovered new exoplanets, although that's not its primary mission. So, the JWST, the James Webb Space Telescope, is equipped with what we call a coronagraph. This is if you wanted to view the sun, right, you would say, oh, I know how to do this, right? I wait for a total solar eclipse for the moon to pass in front of the sun's disk, and then I can look at the sun, look sunward, and see the sun's corona. Well, for astronomers, we don't wait for eclipses. What we do is we say we're going to point our telescope at it, and we're going to have a little disk in the telescope that's going to block the sun's light. We do this for other stars too. We say the James Webb Space Telescope is going to have a coronagraph to block the light from a star, and we're going to try and image the planets around it. It's done that. It's got the best coronagraph of any space telescope ever launched or built. It's setting us up right now. We can see about Neptune size worlds around sun like stars. We could maybe see an Earth like world if it was far enough away from a red dwarf star. But our ultimate goal is to see an Earth like world at an Earth like distance around a sun like star. The James Webb Space Telescope isn't there yet, but already it's taught us so much about exoplanets that we did not expect to find. For example, one of the nearest big star forming regions to Earth is the Orion Nebula. If you see the constellation of Orion, right, you know Orion's belt, and then there are the other bright stars in it. If you look down towards the horizon, below Orion's belt, when you see it, you'll find like a nebulous region. That's known as the Great Orion Nebula. Some people call it Orion's sword, but it does not look like a sword to me. So the James Webb Space Telescope looked inside there, and sure, it found a bunch of new stars and a bunch of new stellar systems. But because it's optimized to look at these long wavelengths of light, these infrared types of light, it can not only see stars, but planets like Jupiter, these big gas giant planets, they emit so much heat, so much infrared radiation that the James Webb Space Telescope can see them too. We have discovered more free floating giant planets without stars, without parent stars like Jupiter has our sun as its parent star. We've discovered more planets without stars just from pointing the James Webb Space Telescope at the Orion Nebula than we had ever discovered free floating planets cumulatively in the history of astronomy.
Wow.
And some of these planets, some of these Jupiter planets, there's actually two of them. They call them jumbos for Jupiter mass binary objects. We did not expect them to exist, and yet they exist. Yet another example of something we didn't even know to look for. And when we turned JWST's eyes onto this object, surprise new discovery.
Oh my God, how cool is that? And now we've all, or not all, but a lot of us have heard that the observable universe is like 14.8 billion years old. Right? And then stars, or we know that because the light from those distant objects has taken that long to get to Earth. Can the James Webb Space Telescope see that far out to the very end of the universe? Is it that powerful?
Well, we can only see as far as the farthest stars and galaxies are, right? You have to remember our universe began with a big bang, and it takes time for the universe as it expands and cools to gravitate, to pull matter into these regions, to clump up, and to have enough mass together that that mass can collapse, form stars, and emit light. So the James Webb Space Telescope, what its superpower is it's allowing us to see farther and farther back towards the Big Bang than ever before. The figure we normally use is we say the universe is 13.8 billion years old. And the James Webb Space Telescope has taken us to the earliest galaxies that it's seeing are between about 250 and 300 million years after the Big Bang. So we're seeing 13.5, 13.55. Maybe someday it'll make it to 13.6 billion years ago. It's seeing the most distant objects we've ever seen, but we still suspect, because the objects it's seeing, they're massive, they're galaxy-like, not individual star-like. We suspect that there's even farther that not only we can see in principle, but that if we push the limits of the James Webb Space Telescope, if we say, observe this ultra distant patch of sky for more and more observing time in longer and longer wavelengths of light, which it can do, we expect it to break the cosmic records that it's already set. We expect it to see farther back in time, farther back towards the Big Bang than anything we've ever seen before.
Oh my, that sounds amazing. And I think I misspoke. I think I said 14.8, and I think you said it was 13.8. What's a billion years, right? It's just a billion.
Plus or minus, right?
Yeah, and who knows? Maybe we'll soon have the James Webb Telescope looking at that additional billion years back. What a cool thing that is. And does that mean that? I mean, it may be a silly question, but maybe does that mean that if it looks back and it sees that things even further and further back, that the age will actually our estimate of the age of the universe will increase from 13.8 to a larger number.
That's unlikely. That's something that people worry about is like, oh my
Yeah.
God, what if it looks and sees back, back, back? But it turns out the farther back you look, you can't go below zero from when you start the clock at the moment of the Big Bang. What it could surprise us in a way where we say, we thought we would only see galaxies when the universe hit an age of 250 million years. But we might see galaxies at 200 million years, or 150 million years, or 100 million years. There is one surprise it's already shown us that I think has knocked the socks off of me and a bunch of other people. Um, and that's that it has found earlier supermassive black holes than we ever thought we'd form. We see very early galaxies, and we have since the Hubble era, where you have a young galaxy with a big supermassive black hole. And one of the things people wondered is what came first, the stars in the galaxy or the black hole, the supermassive black hole in the galaxy? And as the James Webb Space Telescope is seeing earlier and earlier and earlier galaxies, we see that they have fewer and fewer and fewer stars and less and less stellar mass, but they still have these big,
Mm.
greater than a million solar mass black holes at their center. And that's teaching us from the James Webb Space Telescope that, okay, like the story of how we form stars is pretty much similar. to how we thought it would be. But the story of how we form black holes, we've had to revise it. We now think that it's very likely that the first supermassive black holes did not form the way the black holes we see forming today formed. It's not like, oh, we had a
Right.
star, the star lived and died and exploded and collapsed and gave rise to a black hole. No, these supermassive black holes, the earliest ones, they very likely came from a different process called direct collapse, where you have converging streams of cold gas. They can form you a black hole of tens or maybe even hundreds of thousands of solar masses before it forms any stars at all.
Well, yeah,
And that's
that makes
another amazing thing that we've learned just from its first couple of years of science observations.
Yeah, that makes perfect sense. I mean, if we are finding less and less stars out there, then there's got to be, and yet there's all these black holes. It's got to be another way that these black holes are being formed, other than through the collapse of stars. Wow, this has been an extraordinary hour, and it's been a flash of an hour. Just like it seems like it was 8 minutes, but instead it's been 60, and we are now up against a clock. I really want to thank you so much for joining us today.
Thanks
I
for
do
having me on and blazing through
absolutely
this with me. One of the most remarkable things to me is that the universe has always been out there waiting for us
right.
to discover it, and we just had to build the right tool. And once we did, all that
Right.
knowledge that had been obscure to us for generations is suddenly being revealed, not just to people like me, but to all of humanity.
Here we come. Everybody's got to go out right now and get this book. It's Infinite Cosmos, and it's about the James Webb Space Telescope. I've already pre-ordered mine. Everybody is talking about this. It's a must read. So go out and grab that. You can find it at Amazon. You can find it at Borders, not Borders, maybe Borders, but also Barnes and Noble. He mentioned. So go out and do that. Also, of course, go to our website, Access the PodQuest, to check out this episode and other episodes, and find out about all the stuff about the James Webb Telescope. We're hoping to put that up relatively soon. But also come back over here to YouTube, click like, always like the video, always subscribe if you haven't already done so. The more the better. And everybody go there. We will be going ever forward.